Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 13. So, in this we will solve one or two numerical problems in the steady flow into wells, and then we will move on to unsteady flow into wells. First, let us consider one numerical problem. Of steady flow through a fully penetrating well in an unconfined aquifer. So, the data is well diameter, that is 2 RW, it is a 45 centimeter. So, this is the given data. Then thickness of unconfined aquifer, which is a saturated thickness, that is H is 30 meters. I am sorry, it is 25 meters, and the steady discharge, that is Q, is 2100 liters per minute. The observation well radial distances, that is R1 and R2, R1 comma R2, this is 30 meter comma 90 meter. Drawdowns in observation wells, S1 comma S2, that is 5 meter comma 4 meter, and to estimate. So, based on this data, that is well diameter, saturated unconfined aquifer thickness, steady discharge, observation well radial distances. Obviously, this is from center of the well, that is R1 and R2, and the drawdowns in these observation wells, in these two observation wells. So, these are the data given. So, to estimate the coefficient of permeability, 1, coefficient of permeability K, and 2, that is transmissivity, that is T. Okay. So, now we know that for steady flow through an unconfined aquifer, we have the relationship for the discharge in terms of the two drawdowns, or the one is given by pi k h2 square minus h1 square divided by ln of r2 by r1, and here, so this h2 is equal to h minus s2, and in this case this is h is given, which is say 25 minus 4, which is 21 meters, and h1 is equal to h minus s1, which is 25 minus 5, which is 20 meters. So, let us substitute the values. Therefore, this Q, which is given in terms of liters per minute, so that is 2100, and so let us convert this into meter cube. So, divided by 1000, so this will be meter cube per minute. This is equal to pi into k into h2 minus h1 square, that is 21 square minus 20 square divided by natural log of, that is r2 by r1, and in this case this r2 by r1 is r2 is 90 and r1 is 30. So, therefore, K will be given by 2.1 into natural log of 3, 90 by 30 is 3, divided by pi into, so this is 441 minus 400. So, this is 21 square is 441 and 20 square is 400, and so this will directly give the value of K in terms of meter cube per minute. Let me use here the calculator. It is 2.1 into ln of 3 divided by pi into 41. So, this will directly give the answer of coefficient of permeability K as 0.0179. So, this is meter per minute, and the transmissivity T is simply given by K times H. So, this into H is 25. So, this will be 0.448 meter square per minute. So, these are the answers. The K value is 0.0179 and then T is 0.448 meter square per minute. Okay. So, this is how we can use this the data from the well to determine the, to estimate the the formation constants of either formation constants of the aquifer, or if they are given, the steady rate of discharge. And now let us come to the unsteady flow into wells. And here, so the flow is varying with time, and firstly let us consider the unsteady flow through a confined aquifer. Consider a well through a confined aquifer and that too a fully penetrating well. So, wherein the there is an unsteady flow. So, let us draw the diagram. So, this is the ground level, and this is the confined aquifer, and this is the well this is the lower impermeable boundary of the confined aquifer, and this is the upper impermeable boundary of the confined aquifer. And for simplicity, let us consider the thickness as B, and the flow is varying here. So, in this case this is a so this is the unsteady flow through a confined aquifer. Obviously, so here so there is a radial flow, and so consider a fully penetrating well through a confined aquifer receiving radial inflow. Okay. So, in such case the equation is given by the equation for the groundwater flow in the radial coordinates, and here obviously. So, let me also show the water table, the original water table, which is horizontal. So, this is the original WT, and then so this is the drawdown, and obviously, so here at a distance for a general section, the height of this one above this is S, and the drawdown is S, and the height is H. So, now In such case, we can write down the governing groundwater flow equation in radial coordinates, in say cylindrical coordinates, and here you can say this is the homogeneous isotropic confined aquifer. Is d square h by dr square plus 1 by r. So, this is the radial distance r, where the head is h and the drawdown is s. So, this 1 by r into dh by dr. So, this is the second partial derivative of h, the variable head h in the unconfined flow, I am sorry, in the unsteady flow through a confined aquifer, through a fully penetrating well in a confined aquifer. So, this must be equal to S by T, storativity by transmissivity, into dH by dt, and since this is an unsteady flow, so this term, so this dH by dt is a non-zero value. So, this is the governing equation. Now, in this case, and here we can write down this, the total head, the undisturbed head or the piezometric head is capital H, and here we can write down. So, this obviously we can write down the expression, the drawdown small s is equal to the piezometric head capital H minus the variable head in the well along the drawdown curve. So, this is the drawdown curve, this is the unsteady drawdown curve. So, this drawdown S is given by this capital H minus small h. So, for this case, if we it is Theis in 1935 obtained the solution so using electrical analogy as follows. So, that is why this equation is known as the Theis equation. So, the equation is for the drawdown S, the variable drawdown S, which is equal to capital H minus small h, the piezometric head, the constant piezometric head minus the variable head of the drawdown curve H, measured with respect to the bottom impervious layer of the confined aquifer. So, this is equal to q divided by 4 pi into T into integration, that is u to infinity e to the power minus u divided by u into du. So, here, so this term u is known as the well function parameter. So, this is known as the well function parameter. This is equal to R square into S, the storativity, divided by 4 T into T. So, this is the transmissivity T, and then this is the time since pumping, since beginning of pumping. And this R is a radial distance of the where the drawdown is S. So, in this case, so this R square S by 4 T T is denoted as the well function parameter, and its integration, that is e to the power minus u divided by u into du between the limits u to infinity, and this whole thing is known as well function, denoted by WU. So, therefore, the equation for this the solution for the governing equation is the drawdown, the variable drawdown S is simply given by Q divided by 4 pi into T into the well function WU. And here, so this well function, where this well function WU is equal to integration u to infinity e to the power minus u divided by u into du. So, this has been evaluated as a minus 0.5772 minus natural log of u plus u minus u square divided by 2 into 2 factorial plus u cube divided by 3 into 3 factorial minus and so on. So, this is the expansion of this integral. So, therefore, we can write down the, and this is known as the Theiss equation for unsteady drawdown through a fully penetrating well and it is in an unconfined aquifer. So, this fully penetrating well in confined aquifer. Okay. So, this is the Theiss equation, and now let us write down, say that is and here obviously. So, there are the various tables are given for well function value for different well function parameter, and so this Theiss equation can be solved by these graphical methods So, solution for Thay's equation by, let us say this is the graphical methods. So, in this, the first one, let us consider it as the type curves. One is, that is by type curves, 2 by Cooper Jacob approximation, now let us consider the solution of the Thay's equation by the first method, which is by type curves, the graphical method by type curves. So, here what is done is, the expression for the unsteady drawdown is given by Q divided by 4 pi T into the well function W, and we know that. So, this is the well function parameter u is given by r square s divided by 4 t into t. So, that is, we can write this down as t is equal to r square s divided by 4 t into 1 by u. Let us denote this as equation 1 and this as equation 2. So, this equation 1 and equation 2 can be written as log of S, this is the unsteady drawdown S. Obviously, here this Q is the steady rate of pumping. So, here it has not reached an equilibrium. So, therefore, even though this Q is steady, the drawdown S is unsteady, it is varying with time. So, this is equal to log of Q divided by 4 pi T plus log of the well function W. And similarly, so for the second equation, so we can write this as if you take the logarithm. So, this log of t is equal to log of r square into s divided by 4 t plus log of 1 by u. So, here, so these are the two equations. The first, so let us denote this as equation 3, which is simply the logarithm of equation 1, and this is equation 4, which is the logarithm of equation 2. So, here, so this comparison of 3 and 4 will tell us that if we plot S versus T, that is the drawdown versus the time since the beginning of pumping on a log scale, and compare that with the plot of this log of W versus log of 1 by u, and match them so that the both the coordinate axes are maintained parallel. So, in that case we get what is known as the first, let us say this is the plot of log S versus log T, and we get the second plot of log W versus log u, log of 1 by u. So, in this case, so this is log S versus log T is based on the pumping test data, and obviously as T increases, so this S will increase. So, this the number of data points represent the number of readings in the pumping test taken, and then this log of W versus log of 1 by u. So, from the tables, so this is the type of curve. So, here in this this type curve, this one, what is done is, so these two plots are matched. That means, on this, so on the plot of this log S versus log T, this log of well function W and log of reciprocal of the well function parameter 1 by u. So, is superimposed such that both the pairs of axes are parallel in such a way that, so there are the curves more or less match. In such case, what is done is, so this is by trial and error this is done, and then corresponding to any matching point on the curve. So, here, say suppose this is the matching point. So, this is the and corresponding to this we have the log S value given along the log S axis, the log of W value given along the log of W axis, and then this will be log of 1 by u, and this will be log of T. So, if you substitute these values, then, and of course, we have the data, that is log S value is there and then log T value is there, and then so we get this, then we can find out the that is both this log of q by 4 pi t as well as log of r square by 4 t. So, then we can solve for this and get the values of this is so after get the values of the aquifer parameters. So, after obtaining the matching point, ensuring the matching of both the type curves. So, this is type curve 1, which is basically the plot of drawdown versus time on a log scale. In type curve 2 is a plot of log of well function W versus log of the reciprocal of the well function parameter 1 by u. and so maintaining the parallel nature of both pairs of axes. So, we get the matching point, and corresponding to any matching point we can get this log of s, log of w, log of 1 by u, and then log of t. So, once we get all these, so simply substitute the values. So, then we can solve for, so substitute the values of log s, log t, log w, log 1 by u, and estimate storativity S comma t by equation 3 and 4. So, this is the first graphical method for determining the aquifer parameters using the Theiss equation. Now, let us go for the second graphical method, which is the aquifer parameter, that is so this is the graphical solution of Theiss equation by Cooper-Jacob approximation. So, in this case, so obviously here and of course, this has some limitation for u, the well function parameter less than or equal to 0.01. So, in such cases only this approximation can be used. So, in such cases the well function, so here say for u less than or equal to 0.01, the well function, that is W is given by just the two parameters, just the first two terms. Well function is approximately equal to minus 0.5772 minus natural log of, that is the well function parameter, which is r square s divided by 4 t into t. So, therefore, the expression for the drawdown S will be given by q divided by 4 pi into transmissivity t multiplied by minus 0.5772 minus natural log of r square into storativity S divided by 4 t into t. So, this is the transmissivity and this is the time since pumping, and this is the drawdown. So, in this case, so obviously, so this is an approximation. Also for this, the value, the well function has to be less than say 0.01, less than or equal to 0.01. So, in such case, so this is this S can be approximated as q divided by 4 pi into t multiplied by the natural log of, that is 2.25 t t divided by r square into s. So, this is the approximation, and in this case, so what is done is, so here a semi-log plot of drawdown versus time, the drawdown S, the unsteady drawdown versus the time. So, that is it is plotted on a log scale, log of t. In this case, so obviously it will have to, so this is here it starts with it has to start with this one. So, here we get a number of these data points, and this one. So, these data points, the data points having the higher values of time, so they form a straight line, and if we extend this, so this is log of t 0. So, in this case, so basically, so when S is the drawdown, the unsteady drawdown S is equal to 0, then t is equal to t 0, or in other words, in this case, and here we can say that, so that is the, in this case, the argument of this logarithm has to be 1. So, that the natural log of 1 is equal to 0. So, in that case S is 0. So, that is 2.25 t 0 divided by r square into s, this must be equal to 1. Okay. So, therefore, in the Cooper-Jacob approximation, what is done is a semi-log plot of drawdown on the linear scale and then this time t on the logarithmic scale. So, that is plotted, and then so the data points having higher time values, so they will be forming they will be having a linear relationship. So, their this linear relationship is extended backwards. So, to intersect the logarithmic scale of t, and wherever it intersects, so that intercept will give the value corresponding to the time, that is t 0, wherein the drawdown is 0. So, therefore, here what is done is, in the Cooper Jacob approximation, so this t 0 is determined, and once this t 0 is determined, so then we can say that, so the storativity S is simply given by 2.25 t into t 0 divided by r square, and before this we need to know this value of t, and we know that, so the suppose denote this as equation 5, and so based on this equation 5, for any two data points, any two pumping test data points, having drawdowns S1 comma S2 at times T1 comma T2, we have S2 minus S1 is equal to Q divided by 4 pi into T into natural log of T2 by T1. So, here this is equation 6, and from this equation 6 you can write down the expression for this transmissivity T. So, this T is equal to Q divided by 4 pi S2 minus S1 into natural log of T2 by T1. So, this is the equation 7, and by this, and here obviously this S2, S1, T2, T1, they are obtained by the pumping test, and obviously Q is also obtained by the pumping test. So, by the pumping test data where the discharge is constant, only the drawdowns are variables or unsteady. So, therefore, we can estimate the value of transmissivity T, and once we estimate the value of transmissivity, so then substitute this value of transmissivity and the value T0 obtained by the extending backwards the linear portion of the semi-log plot of drawdown S versus the time T. So, we can estimate the storativity. So, this is how we can estimate the parameters, the aquifer parameters, the storativity S of the aquifer as well as transmissivity T of the aquifer. So, this is this we can get the this unsteady this one, and here we should know the approximations. So, it is the assumptions on which this the Theiss equation is based on. So, assumptions for Theiss equation for unsteady flow through fully penetrating well in a confined aquifer. So, let us list these assumptions. So, the first assumption is aquifer is homogeneous, isotropic, of uniform thickness, and of infinite radial extent, I am sorry, areal extent. The second assumption is before pumping the piezometric surface is horizontal. The third assumption is the well is pumped at a steady discharge rate. The fourth assumption is the pumped well is fully penetrating the confined aquifer and the streamlines are horizontal everywhere. The fifth assumption is the well diameter is small, so that there is negligible storage. In the well. And the last assumption is water removed from storage is discharged instantaneously with the decline of head. So, these are the 6 assumptions on which the Theiss equation for unsteady flow is based, and so in the next lecture we will discuss the unsteady flow through wells in unconfined aquifers as well as leaky aquifers. And here we should note that, so of course, I have already made it amply clear. So, the well is pumped at steady discharge. Okay. And so, in the next class we will discuss the unsteady flow through the well in unconfined aquifer. Thank you.